First off, welcome to the e-beam suite at the Nanotech User Facility at the University of Washington. My name is Scott Braswell, and I'm responsible for this instrument that you see here. This is a scanning electron microscope, an FEI. The model is a Sirion field emission scanning electron microscope. So the basic science behind scanning electron microscopy is pretty simple. It's been around for more than 50 years. It's a way of beating the diffraction limit of light. So any item smaller than half the wavelength of light is too small to see with a light microscope. Electrons have a much shorter wavelength, so we're able to image structures that are a lot smaller than the diffraction limit of light in order to see what's going on at that scale, the nanoscale. The main parts of the microscope that you see here are the column, it's a cylindrical piece, the chamber is the square at the bottom, the table that the system is mounted on, and to your left here is the user console where you do all the microscope manipulations. So at the top of the column, in this section right here, is an electron gun. As I mentioned, this is a field emission scanning electron microscope. So the electron gun is essentially a tungsten filament, a very sharp filament. We use a strong electronic field to draw a current off of that filament, and that creates the beam, the probe beam that you use to impinge on the sample and image the sample. Below the electron gun there are condenser lenses, scanning coils for moving the beam, stigmators for adjusting the roundness of the beam, and ultimately there's a probe lens at the bottom, down at about this level. When the electron beam exits from the probe lenses, it then enters the chamber, which is the square section here, and it impacts the sample, where the sample absorbs the energy of those electrons and then re-emits new signals that we use to image the sample. In the table, you'll see across the front are the main power switches for the system. The user doesn't need to adjust these power switches for any reason. They're only for maintenance purposes. You'll also find inside of the table there's a turbo pump that actually helps pump the chamber down to high vacuum. The chamber pressure is on the order of 10 to the minus 5 millibar. There are two different pumps used to pump the chamber down to that level. The main pump is located in the adjacent closet that you don't see, and then the turbo pump is in this table here. Also, there is a pneumatic isolation system in this table to dampen acoustic vibrations so that you don't see any small vibration in your sample while you're viewing it. If I push lightly on the column, you'll see that it adjusts. And the column is floating, and that's how we dampen out some of the acoustic vibrations of people walking into the room or people talking loudly or laughing, so that those things don't show up in the image. To operate the microscope, there are two pieces of software, both run from the same CPU. And you see both of these are open on two different monitors over here on the left. On the right-hand monitor, we have a program called Microscope Control, which is used for all the adjustments on the microscope. And on the left-hand monitor is a database called Scandium, which we use to store the images before we export them for our own use. On the front of the chamber door here, you see there are several knobs and a few handles. This chamber door is held shut by the vacuum inside of the sample chamber. There's actually no latch on the door, so when you vent the chamber to atmospheric pressure in order to load a sample, the door will easily roll open when you pull on this handle. And we'll close it up and pump the air out in order to reestablish vacuum before we start imaging the sample. The knobs on the front of the door are adjustments for the stage. These are the manual adjustments. You can also adjust the stage through the software, and we'll talk about that later. The stage knobs are labeled Y, X, R for rotation, and Z for height in the counterclockwise direction. So all of those aspects of the stage are motorized, and you can control those through the software. The one manual adjustment on the stage is the tilt. Rotation is turning laterally, sort of this direction. Tilt, we can actually also tilt the sample up to 45 degrees. And that's a manual adjustment that's done with this handle and stage lock on the front of the door. The sample preparation happens in this area here. Because we're putting a sample into a high vacuum environment, 10 to the minus 5 millibar, a lot of things that exist in the normal environment as liquids or solids can be vaporized. So we want to keep the sample as clean as possible, which includes keeping our finger oils off of it and also any condensation from the air. We store the samples in a desiccator box to avoid a collection of water on those. And then we also glove up with vinyl gloves to make sure that we don't deposit any material on the sample that we're handling. So out of the desiccator box, I'm just going to take a few standard samples that I keep for training purposes. The inside of the chamber only has one position, or room for one pin mount stub, one sample. So we use this 4-stub adapter in order to expand the stage so that you can look at up to 4 small samples in one sitting without having to vent the chamber to atmosphere and reload it. So each position on this 4-stub holder has a set screw in the side to secure the sample. It needs to be loosened first with an Allen key before you can remove the stub. And then the standard samples I have here for us today, we are going to look at standard gold nanoparticles on carbon and tin spheres. Gold nanoparticles on carbon give you very high contrast, so they're good for looking at the resolution limit of the microscope. And you can see that I'm handling it with a pair of tweezers. Each sample has a small groove in the side. If we were to actually touch the surface of the sample, we would cause a lot of damage to the thin film that's deposited there. So in order to avoid damaging the sample, handling with these tweezers in the groove on the sample holder is the best way to manipulate these. So I'm going to place the gold nanoparticles on the top position. And then I'm also going to put a sample of tin spheres to the right of it. When I mount the sample holder, I always try to put my samples in the same orientation so that once I've loaded it into the chamber and I'm imaging on the microscope, I can remember where everything is located relative to one another. It's a good idea to get in the habit of placing things in the same position each time so that you don't get lost, because when samples are in the chamber and you only see a small area of view, it can be a little bit disorienting, and it might take some time to find samples if you don't know where they're located. So we'll start with these 2 samples today. They've both been kept dry in the desiccator. I've been gloved so I'm not depositing any material on them, and the next thing I'm going to do before I insert them in the chamber is just blow them lightly off with a stream of nitrogen gas to make sure that any dust that's settled on the surface is removed. So this is ultra high purity nitrogen gas, and it's fitted with a gas gun. So what I'm going to do is use a stream of nitrogen from this gas gun to just remove any loose debris from the surface of the sample before we image it. I mentioned the table before. It's tempting to want to use this area here as a work area for your notebook or any things that you carry into the lab, but it's actually a really bad idea to try and use this as a work surface, because any vibrations that you create by putting things on this tabletop are going to be transmitted to the sample. And also there's a lot of delicate equipment actually attached to the chamber, and we don't want to accidentally remove any of these wires or cause any damage. So the only thing I use this table here for is to set the samples while I wait for the chamber to vent to atmosphere. In order to open the chamber door, which is at high vacuum right now, we need to disengage the pump through the software. If I actually pull on the chamber door right now, you can see it's not releasing, and the entire column is actually shifting when I pull. So I don't want to pull too hard. I've just established that the door is secure, and I could verify that again by checking on the software. The vacuum status message reads vacuum OK. Pressure is times 10 to the minus 6 millibar right now. So in order to open the door, I'm going to disengage the pump. And you'll hear the chamber filling with nitrogen. That's nitrogen cylinder that's located in the next room. It takes about 2 minutes for the chamber to equalize to atmospheric pressure, and at that time this door will open easily. There's actually no indication on the software or any place else on the machine that the chamber door is ready to open. You simply have to watch the clock for about 2 minutes to pass, or just keep retesting the door lightly with your fingers on the handle like this. So we've waited long enough for the pressure to equalize in the chamber, and I'm just going to open the door again by pulling on this handle and open it gently until it reaches the stop position. So you can see there's just one position in the stage chamber here for the pin mount sample. I'm going to take the sample that I mounted earlier with the gold nanoparticles on carbon at the top, the 12 o'clock position, and then at the 3 o'clock position is the yellow tin sphere sample. I'm going to put the pin into the hole in the stage, and then there's a set screw on the side of this that I can tighten just with my fingers, and that keeps the holder stationary so that there's no vibration, and it also acts to ground the sample. When you're imaging a sample with the electron beam, the excess current has to go someplace. So if your sample is conductive and you're bombarding it with electrons, it needs to have a pathway to ground to conduct that current away once the imaging is done. By tightening the screw on the side of that pin mount, we're actually completing the ground circuit so that the sample can dissipate the charge after the imaging is done. So that's tightened, sample secure. When I close this chamber door, the sample is actually going to slide in underneath the detector. This chamber will accommodate a sample up to 50 millimeters in length and about 20 millimeters in height. I want to make sure before I close the door, though, that the sample isn't too tall, otherwise it'll run into the detector when I close the chamber door. So I'm going to measure the height of this sample with what we call the elephant ear, just by placing this small gauge on the stage alongside the sample. And you see there's 5 millimeters marked. That represents 5 millimeters of clearance from the detector. So anything that's closer than 5 millimeters to the detector is too tall to be accommodated in this chamber, and it would have to be remounted before we could look at it. But as you can see, that all of these samples are well below 5 millimeters in height, so it's safe for me to close the chamber door. So I'll just remove the elephant ear. And then I'll push the chamber door closed while I'm watching on the CCD camera to make sure that the sample slides in underneath the detector and it's not approaching the height of the detector. Once the chamber door is closed, I'll hold it with one hand and re-engage the pump. It takes about 2 minutes before it reaches vacuum. At that time we can open the column valve and actually view the sample. Most of the software that we're going to use today is located in the first 3 tabs, Magnification, Beam, and Scan. And also the 4 submenus on the right are the blue bars, Vacuum, Beam, Video, and Stage. While the chamber is pumping down, you can do 2 things. The first is you want to center the sample on the stage. And the second thing you want to do is set the beam conditions that you're going to use to image the sample. The first menu here is accelerating voltage, which can go anywhere from 0.5 keV to 30 keV. Lower accelerating voltages are good for fragile samples like biological samples. Higher accelerating voltages give you better resolution. So any sample that conducts well enough to tolerate the high accelerating voltage, 30 keV or 20 keV, you want to use that because it will give you a better image in the end. Spot size then ranges from 1 to 7, 1 being the smallest diameter of electron beam and 7 being the largest. Spot size 1 also has the least current, and so it's again less damaging, and it's also the highest resolution. But because it has less current, it also has more noise, so it's a higher or lower signal to noise ratio. So I'm just going to set this one to 30 keV because our standard sample is a really good conductor. and it can tolerate this without any difficulty. And then you see that under the beam menu, the button has changed to 30 kV, so it reflects the actual accelerating voltage that you're going to use. Also in the data bar down here, you can see accelerating voltage has changed to 30 kV, spot size 3. Open the stage submenu, and that brings up a small map of where my sample is located. The X on this map indicates the center position where the beam is actually coming out. In order to recenter the sample, I'm just going to left double click at the center of the crosshairs, and you'll see the sample move to the center position on the CCD monitor. Alright, after I centered the sample, I need to close the stage submenu in order to see all of the options that are beneath it again. So I shrink the stage submenu, and you see it brings the vacuum, beam, and video back up so that I can monitor those conditions. Under the vacuum submenu, you see this status message now reads vacuum OK, and the pressure is 1.2 times 10 to the minus 4 millibar. The actual reading of pressure in the chamber is not as important as the status message that says vacuum OK. As long as it says vacuum OK, you know the pressure is low enough that you can open the column valve. The upper column where the electron gun is located is at ultra high vacuum. It's usually at about 10 to the minus 10 millibar. If you try to open the column valve before the chamber has reached a low enough pressure, it can crash the vacuum in the column itself. And there's an interlock to prevent that from happening. But that's the indication that we're waiting for, that the chamber pressure is low enough that you can actually open the column valve without affecting the vacuum in the upper column. So once it reads vacuum OK, I can start the beam by clicking on this 5 kV button in the beam submenu. When I do that, you hear the column valve open. That means the upper column is open to the chamber and the beam is coming through to hit the sample. The picture that we get initially is going to be pretty bad. So there are a number of things that we can do to improve this. When you open the column valve and the beam starts to hit the sample, you'll also see this microscope confirm focus box. The computer doesn't know how tall the sample we put in the chamber is, and so it doesn't know how much clearance we have at this time. But once we've focused on the surface of the sample, we'll be taking a measurement of the distance from the pole piece to the sample itself. And then we can calibrate Z, the stage height position, with the working distance being the distance from the pole pieces to the sample surface where the beam is in focus. If this message box is in my way, I can remove it to another monitor or move it to a different position. But I'm not going to click OK until this sample is in focus at 2000x magnification or greater. You can see the beam raster scanning across the surface of the sample. The scan rate can be changed under the scan tab here on the upper left. In the top menu, you see I have 5 different choices, ranging from TV, which is the fastest scan rate, down to slow scan 2, which is the slowest scan rate at 33.2 milliseconds. If you watch the change in the screen as I go from slow scan 1 to TV, you'll notice that the resolution gets a lot worse. TV mode is good because it updates the screen quickly, but it has a very low signal to noise ratio, and so we see a lot more static in this image. Slower scan rates have a lower refresh rate, but they have a lot less noise in the picture. So as long as we're moving the sample around and we want a live update, I'll leave the scan rate on TV. When we want to do fine focusing, we'll look at a slower scan rate that removes all of this noise from the picture. So I want to confirm that the microscope is in focus at 2000x so that I can tell the microscope how much clearance we have in the Z coordinate. Right now it reads Z not calibrated, and it's at a default value of 17.5 millimeters. This measurement is not a true measurement at all. When I get the sample in focus, this working distance will be a measurement in millimeters of the distance to the sample, the correct distance to the sample. The gold on carbon sample is located up here on the positive y-axis, so I'm actually going to move to the center of that sample, and that actually gives us something to see. Focus this by right-clicking the mouse and just moving left to right until I get the sharpest image. Now the sample is much more in focus than it was, and you see the working distance reads 10.7 millimeters, but the magnification is only 97x. I need to get it in focus at 2000 or greater. So I'm going to zoom in by hitting the plus button on the number pad. That doubles my magnification each time I push it. 777, 1553. I'm going to stop and focus because it's clearly blurry right now. And you can see that these defects in the surface of my standard here are more visible now that I've adjusted the focus. So I'll magnify one more time. I'm now at 3100 over 2000. I get the best focus I can, and now the working distance reads 13.5 millimeters. This is an accurate measurement of how far the sample is from the pole pieces. So I'm going to calibrate that height of the stage by clicking OK in this box. And you can see that it transfers the working distance into the Z coordinate over here. Once I know how far it is to the sample and I've calibrated the stage height, I can reduce that height because the imaging is always going to be better at a lower working distance because there's less atmosphere for the beam to travel through. Ultimately, I want to do my imaging at about 5 millimeters working distance. As a safety measure, I'm going to reduce this to 10 millimeters first, recalibrate the stage height, and then move to 5 millimeters. So to adjust the stage height, I click on the drop-down menu in the Z field, and I select the final clearance that I want from the detector. Right now we're going from 13.4 to 10 millimeters. And then to initiate the move, I click on this Go To button. And I move the mouse to the upper left corner and watch on the CCD camera as the sample approaches the detector. If the sample gets too close to the detector, there's a cancel box that will open in the upper left corner, and I want to be ready to click on cancel so that the sample doesn't actually impact the detector. If you're careful about following the protocol and the sample is in focus before you move it, you shouldn't need to cancel the vertical movement. But in case there's a problem, you accidentally focus on the wrong part of the sample, for example, you want to be ready to stop that vertical movement before any damage is done to the machine. So my working distance now is 10 millimeters, and the resolution of the stage motor is on the order of microns, so it doesn't go to exactly the position that I want it to go to. And after I've told it to move to 10 millimeters, I need to refocus and actually tell how high it went, because it'll be slightly off from 10. I'm going to focus again to get the best possible focus. I can see that I'm off by less than 1/10 of a millimeter in this case. But I want to recalibrate the height of the stage. To get the dialog box back, I click on Z, forward working distance. And again, I want to confirm that the sample is in focus at more than 2000x by clicking OK. And you see that it's updated the Z height with 10.049 millimeters. So I was off in my initial movement by 0.049 millimeters, which isn't much under normal circumstances, but it makes quite a difference in the focal length when we're actually trying to look at a sample. So I'm at 10.049. I'm going to drop this stage clearance now down to 5, and I will initiate that movement, and I'm ready to cancel in case the cancel box opens. We're at the final working distance, so again I'll focus, and I can't see very clearly because the beam conditions haven't been optimized yet. Even though the sample's in focus, if the beam isn't perfectly round, we'll get a distorted image, and that hurts our resolution quite a bit. When the beam is optimized, we should be able to resolve down to about 10 nanometers, 10 nanometer size structures on the surface of the sample. So I'm going to zoom out, and I'm going to move to a position that has better contrast. So you see on the edge of this group of nanoparticles, there's a blank space. That's black carbon. And I'm just going to zoom in to this area where I've got both the bright and the dark in the same field of view. And I'm going to try and focus the boundary between the two as best I can. You can also see that some of the defects, blemishes on the sample become visible when I'm in the right focal plane. The next thing I want to do, I'm in focus at 6,000. I'm at my final working distance of 5 millimeters. I want to zoom into 10,000 or more, and we'll do the beam optimization. See that when I focus, the sample actually moves. I want to eliminate that movement and make it easier for me to get the correct focus. So under the beam submenu, I click on the lens modulator button. That modulates the focus of the sample. It should be flashing in and out of focus, but not moving laterally the way you see it moving now. This means that the beam is not going directly to the center of the lens, but it's going through the thinner edge of the lens. And that's displacing the sample image below it. So I'm going to pull the beam towards the center of the lens by clicking in this lens alignment box. It's a left click with the mouse and I hold it. I see the picture is moving left to right, so I know that the beam needs to be dragged either to the left or right. I don't know which. So I'm going to try right first. And I'm just going to take a medium-sized step to see if that helps. And it actually did eliminate a lot of the side-to-side movement. Now I see that there's some vertical. So I'm going to try up, and I see that it's actually gotten worse. So I'm going to try the opposite direction now, adjusting the beam down. And again, it's still moving, some X component and some Y. I'm going to try and eliminate the Y component first. And I see that's getting worse, so I've gone too far. And I back up. I back up just a little bit more. You see it's moving left to right. That made it worse, so the right should make it better. Now when I have it so that it's stationary, I can release the mouse and the lens alignment has been fixed. And then I turn off the lens modulator by clicking this box again. Now when I focus, the sample is stationary, it doesn't move at all. I'm going to change the scan rate now to something slower because I'm trying to get a sharp focus on the sample. You see that under slow scan 2, a lot of the noise is gone from the picture, but I have a distortion that I need to get rid of here. There are a lot of streaks in this picture that all seem to be pointing from the upper left to the lower right. That's an artifact of the beam that needs to be corrected. In a normal sample, you wouldn't find that kind of uniformity. So those streaks mean that the beam is not perfectly round. Instead, it's more of a football shape. And I'm going to adjust the shape of the beam by using the stigmation adjustment. Now, it takes too long to update the whole screen under slow scan 2, so I'm going to choose select area function, which only updates a small area of the sample. And you see it updates more frequently, so I can get quicker feedback to what I'm doing. Focus the sample. And you can see that I'm stretching the sample from upper left to lower right. And when I back off the focus, I start to stretch it from the lower left to the upper right. The correct focus is actually in between those two distortions, where everything is as round as it could be, even though that's a lot fuzzier picture than we would like. The focus is correct, and the reason why this image is blurry is just because the beam is not perfectly round. So I can adjust the roundness of the beam by clicking on the Shift button on the keyboard and then right-click the mouse. That engages the stigmation. And then I'm going to adjust both the X and the Y axis one at a time to get the clearest picture possible. I'm going to start with the X axis. You can see as I move to the left, it gets a little bit clearer, and then it starts to get blurry again. When I come back to the right, it starts to get blurry again. The best position on the X-axis is about here. I'm going to keep that X location and try and adjust the Y next. Positive Y. I go too far, it gets streaky again. Negative Y, it starts to get blurry. The best location I can find is about right here. I release the mouse, turn off the selected area, and see what the whole field of view looks like. Now you can see this frame that's been deposited on the sample. When you spend a long time with the electron beam imaging a small area like this one, it's a box about 2 micron per side, the surface will get charged a little bit and you'll deposit contamination from the chamber onto the surface of the sample. So after you've imaged an area for a little while, you want to move away from this area to a clean spot. I'm just going to move a little bit to the lower right, and then I'm going to repeat the adjustment that I just made at a higher magnification. So I'm at 11,000. I'm going to increase this now to about 50,000. Now I want to try and get it in focus again. I'll use the select area so it updates faster. Focusing is just right-clicking the mouse. I think at this position all the particles look as round as they can be. If I go too far to the left, it gets blurry and stretched. If I go too far to the right, I get the same thing, blurry and stretched. This is probably the best location for the focus. And now I'll stigmate again. Shift and right-click the mouse. I'm going to repeat those same adjustments at 100,000x this time. And to speed up the process, I'm going to restrict the field of view to a small box. I start by focusing to eliminate the streaks that you see. Right now I have horizontal streaking. I focus back to the left, that disappears. And then I'll start to see vertical streaking. The correct focus is right in between those two distortions, where everything looks round and plump. And now I can improve this image by correcting the stigmation, the roundness of the beam. So I hold the Shift key, hold the right mouse button, and then I look for the best location first on the X-axis and then on the Y-axis. Now I feel like I've made the best adjustment I can. I'm going to open the field of view. And because I've been imaging this area with a really dense charge, you see that from the scale bar, this box that I was viewing is only about 200 nanometers per side. So all of the charge is scanning over a very small area, and this has become really contaminated and black. Now I'm going to move to a clean area so we can actually see away from this area of contamination what the sample looks like. If I wanted to pick an exact magnification and I then have a round number in this data bar, then I could pick it from this magnification tab, and the microscope will go directly to that magnification. I'm going to center this defect on the sample by using one of my stage movement tools. You see the one that's active right now is the stage get mode, and that's the crosshair, the icon that I have on the mouse right now. If I want to bring something to the center with the get mode, I just left double click on the feature and it brings it close to the center of my field of view. Another stage movement tool we use a lot is the donut tool, technically called the tracking mode. If I activate tracking mode, you see it brings up this donut on the screen. At the center of the donut, in the hole, my icon changes. In the top half of the donut hole, I have a plus. And that's a fine zoom in when I left click. In the bottom half of the donut hole, I have a fine zoom out. Those are much smaller steps than you get by using the number pad. This is a gross zoom in, the plus sign, and a gross zoom out, the minus sign on the keyboard. So I'm at 11,000. I want to bring this feature to the center using the get mode. So when I left click anywhere outside of the donut hole, you see the stage will track that direction. And you can see they're pretty rough movements. Under high magnification, you can actually see the step size of the motor. Once I have it in the center, I'm going to focus one more time. And now I'm going to adjust the lens alignment on the microscope. To capture an image, first thing I usually do is auto-adjust the contrast, and then I push F2 on the keyboard to capture the image. F2 is a macro that scans the whole field of view in the slowest scan rate. It's actually going through slow scan 4 right now. At the end of the field, it's going to freeze this image and block the beam. So the sample isn't being exposed to the beam right now, and we can take our time in looking at this image. But this isn't saved, it's only frozen in the microscope control. In order to save it, we need to transfer it into our database called Scandium. And once it's stored over on Scandium, I'm going to go back to live imaging by unfreezing this picture. Once the macro is finished, you can transfer that image into the Scandium database by picking your folder from the left menu and then picking the camera with the yellow tube behind it, snapshot to database Scandium. That brings the image over to the database, and then it prompts you for a sample name. Click Insert, and now our image is saved in the Scandium. So we can return to the microscope control and continue imaging. After you've imaged one area of the sample like this, if you want to move to a new area, you would change over to the stage track mode, change the scan rate to TV, and then just left click anywhere outside of the donut hole. And you can see we're moving the sample to the left, so we're imaging more to the right side of it now. And we're only moving in really small steps of about 1 micron right now. If you want to move faster, you need to zoom out, and you can move to a new part of the sample. And you can also track where you're moving by watching the X on the stage table, and that will reflect what part of the sample you're imaging to. When you get to a new area of interest, you magnify, and when you find a feature you want to bring to the center, you change back to the stage get mode, the crosshairs, and double click on that feature. And then when you zoom in, bring it back to center and focus. If I want to take measurements, I want to work from a frozen picture so that there's no movement. So I'm just going to scan this image, and then I'll show you the measurement tool. So in addition to the scale bar across the bottom here that measures 200 nanometers, I can also use this ruler tool, which brings up a measurement menu. I can measure along the x-axis, y-axis, or random points. And you see that my icon right now is a crosshair. I find it hard to see the edges of the particle through the crosshair, so I like to change to the pointer. I'm going to measure a horizontal nanoparticle along the horizontal element. I'm just going to left click and drag from edge to edge. This is measuring 16.2 nanometers. Then if I wanted that to appear on the picture, I just click Accept, and you can see that my picture is labeled now 16.2 nanometers is the diameter of this individual particle. After I've labeled the picture, I can print this image with the labels on it by going to In-Out, Video Print. And we have a thermal printer that will produce that right here. If you wanted to save an image that had these labels on it, instead of using this measurement tool, you'd use the Scandium measurement tool. And down along the left margin here, you see there are different axes: vertical measurement, horizontal measurement, or arbitrary line. I'm going to zoom in so that I can see better. And you can see that my image is getting pixelated, so I won't go any further into it. And I'm just going to take a horizontal measurement using Scandium. You left click the left side of the particle, and then left click the right side of the particle. It gives me the length of that particle is 38 nanometers. When I'm done with the measurement, I have to push Escape to drop that measurement tool, and then I'm going to zoom out, and I can save this image with the label on it. The measurement is already inserted onto the picture, and now I need to burn it into the overlay to save it. It gives me a warning that all of the image beneath that label and beneath this mark is going to be lost. And I'm okay with that at this point because I'm going to save a raw image as well as a labeled image. That way I don't actually lose any data. So I'll click OK and then File, Save As. We have a network drive where we save all of the images. So in order to access that network drive, I'm going to go to the desktop link. And the drive is called Ntuf Users on Bleach. So I open this network drive and I see there are folders for each user, which I'm going to hunt down my own folder, open it, and then within my folder I'm going to create a new folder with today's date. And that will keep my images organized. You see that 10/14/09 is here in the left corner. Now that I have that open, I'm going to click Save. And it saved that image now in my own folder so that I can get to it later. Not all of our samples are exactly the same height, but for safety purposes we want to make sure they're within a couple millimeters of the same height of one another. That way when I move over to the next sample holder, I'm not in any real danger of hitting the detector. To be sure that I'm not too close to the detector, before I move over, I'm actually going to drop the stage back down to 10 millimeters. Gold nanoparticles at 12 o'clock, and I put this tin sample at 3 o'clock. And those clock positions I was referring to are from this stage table. So when you put the sample holder into the chamber, samples that are facing away from you are at 12 o'clock. They'll be along the positive y-axis here. And the 3 o'clock position is the positive x-axis here. So I can either make a mental note of where those are located, or I can draw myself a map before I close the chamber door so that I know where things are going to be on this table. And then I'm going to move it over to the next sample by just double clicking on this stage table along the positive x-axis where I know that next sample is located. So we're moving now to the tin. And now I don't know exactly what the clearance is. It's 10 millimeters from the gold on carbon sample to the detector. But the tin sample may be taller or shorter. So I'm going to recalibrate the stage height by repeating the procedure we did earlier. When the stage track mode is on, I can go up in the X direction, and we're moving about this fast when we're using that donut tool to drive around. Here's a little bit larger step in the Y direction, and then moving from the gold to the tin sample, we dropped the stage down and then we moved it laterally like this in both the X and the Y. One thing we didn't do that's pretty cool is rotation. So this changes the relative positions of your samples. So you can lose a sample if you're not paying attention. You can rotate it out of position. So the tilt, there's a black mark here on the top that gives you just a course adjustment. And right now you can see it's set at 0. You can also read the tilt from the T field here in the stage menu. And that actually reads it 0.2 of a degree, so this is more accurate. And to adjust the tilt, we just want to support the weight of the stage with our hand here and unlock the stage screw, and that frees it up for rotation. So I can tilt the sample down up to 45 degrees in this direction. While I'm doing that, I want to be watching the CCD camera to make sure there's still clearance over there. And then when I've gotten it tilted to the angle I want, I just reset the stage lock and it'll hold that angle. We like to keep the microscope set at 5 kV, spot size 3, when it's not in use. So if we had changed the accelerating voltage or the spot size before we shut down, we would set them back to these default values, 5 and 3. And then you turn the beam off by, again, clicking the 5 kV button in the beam submenu. And you'll hear the column valve close. That means that the sample chamber is sealed off from the column, and we can vent it to atmospheric pressure. And now I'll disengage the pump by clicking vent, and then it always asks if you're sure. I'll click OK. And then the CCD is going to show you the sample drops back down to the bottom. I'm just going to open the door, again by pulling on this handle. And then I'm just going to loosen the set screw. Take the sample out for later. Close that again. And then I would pump it down to vacuum.